Hello students, now in this video we will start chapter 2 of graph theory, that is connected graphs. Connected graphs. Now in chapter 1 we define basic terminologies of graph and introduced concepts like matrix representation of graphs, operations on graphs and isomorphism. In this chapter, we will study concepts like walk, path, cycle, etc., which would help us to understand the definition of connected graph. We also study isthmus and cut vertex and algorithm to find shortest path between two vertices. So now, first of all, walk, path and circuits. Walk, path and circuits. Let's see these. What are these? Now, definition. Let G be a graph. A walk in a graph G is defined as a finite alternating sequences of vertices and edges. V0, E1, V1, E2, V2, E3 and so on up to Vn minus 1, En, Vn. Beginning and ending with vertices. Beginning and ending with vertices in which each edge is incident with two vertices immediately proceeding and following it. Okay. A walk in a graph is denoted by W. Also, the walk V0, E1, V1, E2, V2, E3 and so on up to Vn minus 1, En, Vn may be written as V0, V1, V2 and so on up to Vn minus 1, Vn and is called V0 to Vn walk. The vertices V0 and Vn with which walk with which the walk begins and ends are called the initial and terminal vertices If V0 not equal to Vn, then walk is called an open walk. If beginning vertex and terminal vertex in initial and terminal vertices are different, then walk is known as open walk. Otherwise closed walk. That is if V not equal to Vn. Right? If V not equal to Vn, then that is known as a closed walk. Then another definition, that a walk in a graph in which no edge is repeated is called a trail. Definition. Next one. A closed walk or the closed trail, let it be trail. A closed trail is called tour in a graph G. Okay, one more definition. The number of edges in walk is called length of the walk. Okay, now let's see one example and let's check whether some walks we will write. We will check, are they trail, tour, or really they are open walk, closed walk, which are they? Okay, this graph G is given here, where consisting 5 vertices and 6 edges. Okay, now this walk 1 is given. Look at, that is V1 E1, V2 E2, V3 E3, V4 means as such we will go V4 E4, so V5, then again E4, then V4 E6 and V2. Here it will be completed. Now here it is a sequence of vertices and edges, so it is a walk. Now again V1 and V2 are not same, so it is an open walk, we can say. But now here this edge E4 is repeated, fine, that's why it is not a trail. Okay, so no question about tour also, so is a walk. Simply I can write is a walk. Now look at this, it is V1 E1, V2 E2, V3 E3, V4, E4, V5. So now it is here no edge is repeated. So this is a walk, but is basically a trail. Is a trail. No one edge will repeat. That's why trail. Now this is V1, E1, V2, E2, V3, E3, V4, E6, V2, E1 and V1. So here E1 is repeated, so no, it is not a trail, but V1 are same, so is a closed walk. Closed walk. Okay. Then the next one, V2, E2, V3, E3, V4, E6, V2. So here it completes. So is a here again initial and terminal vertices are same. So is a closed walk, but basically again the edges are not repeated. So is a tour. Is a tour. Fine. Now the next definition. A walk in which any vertex is non-repeated. Any vertex is non-repeated. Hence, there is no repetition of an edge also, of any edge. Not vertex is not repeated, so obviously the edges are not repeated, is called a path. Such a walk in which vertex is not repeated, so obviously edges are not repeated, so such a path is known as what? Such a walk is known as a path. For example, in this graph G, we can take V1, E1, V2, E2, V3, E3, V4 is a path. Here the vertex is not repeated. Okay. For example, V1, E1, V2, E2, V3, E3, V4 is a path in G. In this graph I am taking. Okay. Again, another definition, a closed walk in which no vertex except its terminal vertices. Except its terminal. If initial and terminal vertices are same, then the walk will be a closed walk. So no vertex except the terminal vertices appear more than once. Is called a circuit. Circuit, or it is also known as cycle. A closed walk where no vertex is repeated is called a cycle. Now for example, here we can take V1, E1, V2, E2, V3, E3, V4, E4, V5, E5, V2. As such we can come, right? Or V2, E2, V1, E1 we cannot take because it will be closed. So V2, E2, V3, E3, V4, E6, V2. That is also this tour. This tour is also a cycle. V2, E2, V3, E3, V4, E6, V2. Here no other vertices are not repeated, while only initial and terminal vertices are repeated. So is a cycle. Is a cycle. Fine. Now write down few notes. So first, the number of edges in a path or cycle is called length of that path. Length of that path or cycle. Okay. Another note, a path of length greater than 0 that begins and ends at the same vertex is known as circuit or cycle. Okay. Third, self loop is a circuit. Another note, a regular graph of degree 2 is a circuit. Fine. Then in a graph G there exists a path from U to V if and only if there exists a walk from U to V. Okay. Here a graph G, there will be a path if and only if there exists a walk. Obviously a walk is nothing but the path with no repetition of vertex. Such a walk is known as a path, right? Also these are obviously all these are nothing but the notes obtained from the definitions. So the path of length greater than 0 that begins and ends with same vertex is known as a cycle. So is a closed walk, that's why it is of length greater than 0. Self loop is a circuit that is of length 1, right? So that's why a path of length greater than 0 is nothing but the circuit, right? A regular graph of degree 2 is a circuit. That will be a rectangular graph. Fine. Now the next one, connected graph. Connected graph, let's see the definition. An undirected graph G is called connected if there is a path. There is a path between every pair of distinct vertices of the graph. There is a path between every pair of distinct vertices of the graph. If G is not connected, then it is said to be disconnected. In a disconnected graph, there is at least one pair of vertices which is not connected. For example, now look at this one. Suppose this is G1 and here as such, suppose given A, B, C, D. Suppose here V1, V2, V3, V4, V5. This is G2. So here this G1 is connected and G2 is disconnected. There is no path between V2 and V3. Also from V1 to any other vertex, right? So it has 4 vertices, 4 edges, but here this doesn't have a path in between these vertices to any other one. V2 to V3, V2 to V4, V2 to V5, there is no path. That's why this is disconnected. This is what connected graph. And this is disconnected graph. Fine. Now another definition: a connected subgraph H of a disconnected graph G. Which is not properly contained in any proper connected subgraph of G. Subgraph of G is called maximal connected subgraph or component of G. Now let me take an example here. What does it say? Such a subgraph of disconnected graph G which is not properly contained in any proper connected subgraph of G is called maximal connected subgraph, or it is also known as a component of G. Suppose G is this graph. Suppose this here as such. So let it be, let V1, V2, V3, V4, V5, V6, V7, V8, V9. So this is G. Now let me take here that suppose here one more edge, let's we join. Suppose it is V6, V7, V9. Let it be H1. Okay, then another, suppose let it be V1, V2, V3. So it is H2 suppose, and suppose I am taking this V7 to V8 suppose. Let it be H3. One more, let me take V6, V7, V8, V9. This is H4 suppose. Now look at this graph G. Here I have been taken few components of it. So now V6, V7, V9. Look at this. Few subgraphs of it. Which are these? Are components? Let's check that one. So now here this H1 is in this H4, right? This is a subgraph, but it is in H4. So it is properly contained in that one. That's why this is not a component here. Also, look at this V7 to V8. There is no such a thing. Sorry, here let me take H3. Let it be V2 to V3. Okay, look at this V2 to V3. This part is here present. That's why this H3 is also not a component. This is also not a component. But these are not properly contained in any other subgraph. That's why these are what the components of it. Okay, these are subgraphs, but these are not components, while H2, H4 are components. So here H2 and H4 are components. These are what? Components. Now, two notes. First, a graph G is disconnected if and only if its vertex set V can be partitioned into two subsets, V1 and V2, such that there exists no edge in G whose one vertex is in the subset V1 and the other in the subset V2. Another note, a simple graph with n vertices and k components. A simple graph with n vertices, k components cannot have more than n minus k plus 1 upon 2 edges. Now, this is very true that here a graph is disconnected if only vertex set can be partitioned into two subsets such that there is no edge in between, means whose one terminal is at V1 and other will be in V2. This is just like a previous example in which we have taken three different parts, that is what a disconnected graph. So no two vertices are connected to each other, that is what a disconnected graph. So here we will stop for this. In next video we will see counting paths between vertices and some examples. Thank you.